continue with the next part of the lecture, this is semiconductor photodiodes. In the last class we began with the semiconductor photodiodes and primarily we have discussed with the pin photodiodes, and in this class we will continue and discuss the second important class of photodiodes, which are the APDs or Avalanche photodiodes. Before I proceed with the lecture, in the last class we had a quiz, that is the last quiz, quiz 12. The commonly employed semiconductor material for photodetectors in optical communication receivers is indium gallium arsenide. Give any two important reasons for the choice of this material. This was the quiz, and the answer is of course any two. So, you have several advantages and several reasons why one uses indium gallium arsenide, but the most important reasons are because indium gallium arsenide has a relatively large quantum efficiency or responsivity in the low loss window, that is around 1.55 micrometer in the low loss window for optical communication. Here we are referring to optical fiber communication, and as you know, the silica based optical fibers have the lowest loss at 1.55 micrometer, and the window, the low loss window around 1.55 micrometer is where one uses the WDM communication systems or the DWDM communication systems, where a large number of wavelengths are packed into the low loss window centered around 1.55 micrometer. And therefore, this is the detector which is widely used primarily because of the large quantum efficiency. We may recall that we in the last class we have discussed the quantum efficiencies. This graph we had shown this graph here of quantum efficiencies. So, we can see that silicon has a very good quantum efficiency in the range up to about 1 micron or less than that, here about 90% goes up to 90%, whereas indium gallium arsenide has a large quantum efficiency around 70% or so in the range of about 0.9 micrometer here right up to 1.77 micrometer. And as you can see here that at 1.5 and at around 1.55 the quantum efficiency for indium gallium arsenide is very high. Although germanium can also detect, as you can see here, germanium also has a responsivity here, but silicon has indium gallium arsenide has the largest responsivity, and that is one of the main reasons why one goes for indium gallium arsenide. The second important reason here, the second reason is also that for high speed detection, the second reason here we have listed the second reason, for high speed detection due to high mobility of electrons in indium gallium arsenide. In the last class or in an earlier class we had discussed that the mobility of indium gallium arsenide for electron mobility is of the order of 14,000 centimeter square per volt second, compared to silicon, germanium, which have a few thousand of mobility of electrons. So, a large mobility implies a large saturation velocity. Even at relatively smaller electric fields one can get a large saturation velocity, and hence the speed of the detector becomes, the transit time gets reduced and the detector becomes a high speed, because optical communication, in optical communication we are talking of 10 Gbps, 40 Gbps and so on. You need high speed detectors to detect the incoming pulses. So, these are the primary two reasons why one goes for indium gallium arsenide for optical fiber communication. So, today we continue with the talk on semiconductor photodiodes. So, before I proceed with the part 2, that is avalanche photodiodes here, a small topic remaining there. In the last class we discussed the design characteristics of photodiodes, and in particular we discussed that there are two modes of operation, photovoltaic and photoconductive mode of operation, and we have discussed in detail the design characteristics here and how to choose the load resistance. And here is the summary that we had, that choose large RL, the load resistance for high output voltage, suitable for low power incident on the detector, that is higher sensitivity. However, choose small RL for large dynamic range, that is for linear output versus optical power input characteristics over a wide range of power. Typically 60-70 dB dynamic range is possible. So, a small topic of importance is also speed of response of pin photodiodes here, and the equivalent circuit of a typical photodiode here is shown in this diagram here. This is a current source with a resistance across here, the diode resistance, the reverse diode resistance, which is a very large resistance, and a junction capacitance here, the diode capacitance, which is the junction capacitance CD or Cj, and a series resistance and the load resistance. This makes the equivalent circuit of a photodetector. The load resistance RL is this is much smaller than RD, because the reverse bias, under the assumption that RD is much larger than RS and RL, we can show that the rise time is given by TR is equal to 2.19 RL into CD, and the 3 dB bandwidth of the photodetector is 0.35 by rise time, and the frequency, the cutoff frequency or the 3 dB frequency, as you know, the photodetectors respond right from DC, all the semiconductor photodetectors respond from DC, and this f3 dB here refers to the higher cutoff frequency, and that is given by 1 divided by 2 pi RL into CD. RL here is the load resistance and CD is the junction capacitance, approximately given by this formula. The important point to see is the 3 dB cutoff frequency depends on the load resistance RL and the junction capacitance CD, and therefore for high speed detection reverse biasing very much helps. Reverse biased pin diodes are used for high speed photodetectors. CD here should be very small, because it is in the denominator if you want to have a large cutoff frequency, typically few picofarads, and CD will be small if you have a small area and large reverse bias. Large reverse bias leads to a small junction capacitance, because the depletion region, width of the depletion region increases. Small area of the photodetector here, as you know, the junction capacitance, the capacitance, a parallel plate capacitor has a capacitance given by C is equal to epsilon 0 A by D. A is the area and D is the separation between the capacitor plates, and a large reverse bias leads to a relatively large D. We can look at this diagram here. So, it is a PIN diode which is reverse biased. The depletion region extends under reverse bias, relatively large reverse bias. The depletion region extends over the entire intrinsic region here, entire the D is extending over the entire region here. So, the D is relatively large, which means C is small, and if we make a small area detector, then this C will be further reduced, and therefore, to reduce D one applies a large reverse bias and takes a small area detector. Typical area is 0.1 or 0.01 millimeter square is the typical area of small area detectors, whereas large area detectors can be 1 centimeter square when the speed is not important, but sensitivity is important, one chooses large area photodetectors, large area pin detectors. So, RL should be very small, typically 50 ohm, as I mentioned in one of the earlier classes. The data sheets typically specify the rise time at 50 ohm load resistance. If you change the load resistance, then the rise time would also change. So, typically TR is about 1 microsecond for normal PN diodes, and T rise time is of the order of 1 nanosecond for PIN and APDs. Silicon APDs with the rise time less than 0.1 nanosecond are also available. With this, we switch to the next device, which is the Avalanche photodiode. It is basically a PIN diode, but with a large reverse bias, which provides avalanche gain. So, relatively large reverse bias, Avalanche photodiode, relatively large. We will see what kind of numbers for the reverse voltage is applied. This depends on the material, silicon, germanium, indium gallium arsenide. It depends on the material, what is the reverse bias, what order of reverse bias are applied. I will give some numbers towards the end of the talk. There is a built-in gain in the device due to carrier multiplication in the depletion region by the avalanche process. We will see what is this avalanche process. So, built-in gain in the device. Typical photocurrent gain M is of the order of 10 to 100. So, M here is basically the ratio of primary photocurrent to the current which is generated. So, the photocurrent IP in the external circuit after the avalanche process to the primary photocurrent is M, typically 10 to 100. It is higher sensitivity. So, this gives because of the current gain, the sensitivity is higher. However, it is little bit more noisy because the avalanche process by its very nature is noisy. It is a relatively random process, and therefore, we have a relatively noisy output. So, here is the energy band diagram of the PIN structure here. Because of the large reverse bias, we can see that now the potential barrier here or the potential energy diagram has a large slope here in the active region, in the depletion region, because of the large reverse bias. So, this is the P side, this is the N side, EVP, the valence band energy and conduction band energy. As because of the large potential slope here, potential energy slope, an incident photon that generates an electron and hole pair here, a hole and electron. As the because of the large potential energy slope, the electron goes down the slope, travels down the slope. As it travels, it is getting accelerated because of the potential energy slope here, because of the high electric field, it is dV by dx. So, high electric field, which the kinetic energy of the electron is such that it knocks down another electron and creates additional electrons by the avalanche process. It knocks down another electron from a bound, another bound electron, and creates an electron and hole. Similarly, the hole which is getting accelerated up here, hole is getting accelerated in this direction. The hole getting accelerated also creates secondary electron hole pairs, electron hole and electron pair. So, this is the primary hole which has created a secondary pair, which leads to carrier gain, that is increase in the number of carriers by the avalanche process. So, I have shown just two events, one here at this end and one here, but actually there are large number of carrier multiplication events take place as the carriers travel up and down the potential energy slope. So, this clearly illustrates the increase in the carriers, increase in the number of carriers due to the avalanche process. The gain characteristic of a typical APD is shown here, reverse voltage, the numbers are here now, typically 100, 200, 300 volts are applied for as the reverse bias, and what is plotted is the gain, the current gain M is defined here, I m divided by I p. This is the gain after the multiplication process, current after the multiplication process, and this is the primary photocurrent due to the incident photon. So, at 20 degree centigrade, for example 20 degree Celsius, the current gain increases initially as the voltage increases, and then it goes over to a relatively slow region here, a slow rise here, and then finally it again goes rapidly, and this is where the avalanche process is so rapid that the device would lead towards breakdown. So, this is not the operation region, the operation region is here between these two lines. So, typically for this example it is typically between 100 and 300. Normally the operating voltage is specified like 220, 250 volt DC. So, this characteristic shows the current gain here for an APD. At a different temperature, say at a higher temperature, a characteristic varies. So, it is indeed temperature sensitive, and the characteristic changes because at higher temperature, at a higher temperature here we have a more agitation of the atoms in the lattice, and therefore, the electrons and holes undergo more collisions, that is the separation between, that is the spatial separation or the average length. So, let me discuss in the next slide here and then come back. We can see that there is a parameter called impact ionization coefficient alpha, which is defined as 1 divided by L internal average. This here refers to a collision, the distance, the average distance travelled between two successive collisions. So, this is L impact. So, the average distance 1 by L impact is called the impact ionization coefficient. This is per unit length, and this depends on L. If you have, for example, if you apply if the temperature is higher, then the electrons do not have enough energy between two collisions, and therefore, the number of collisions which lead to generation of additional carrier pairs decrease, and therefore, the current gain decreases. So, this is just an example to show that it is temperature sensitive, and higher the temperature, then lower will be the current gain. In fact, most of these detectors are cooled. One can cool this further down, and the curve would qualitatively look like this. It will go up, the characteristic will go up if you cool the detector further, and it will be less noisy as well. So, we come to this discussion here, impact ionization by electrons and holes in an APD. What is shown here is the same APD PIN. The incident photons here generate electrons and holes in this region, that is the catchment region. Here only electrons are shown. The electrons are swept towards the positive potential here, that is the negative end, which is reverse bias diode. So, there is a positive potential at this end. So, the electrons are accelerated in this direction. When the electron gains sufficient energy, it leads to generation of a secondary electron and hole pair, which further travels in this direction and gets the electrons travel in this direction, and of course, the holes travel in the opposite direction. I have not shown holes in this diagram, holes are shown in the next diagram. First, please see only the first diagram, where electrons, the secondary electrons are also getting accelerated and creating more and more electrons as they accelerate towards the positive end. The holes on the other hand are accelerated to the other end. As you know, electron mobility is higher and therefore, they gain a higher velocity in the same electric field. When the electric field magnitude is the same, they gain higher velocity, much higher velocity, and therefore, much higher kinetic energy and lead to rapid avalanche of further carriers. Holes get accelerated to the other end, and as they proceed, whenever they gain sufficient energy, they also generate additional electron hole pairs, and the holes continue to proceed towards the negative end, that is the p end. The impact ionization coefficient, this is at a given temperature. At a given temperature, the impact ionization coefficient is defined as alpha is equal to 1 divided by average length, average distance between two successive collisions. In silicon, for example, alpha E, that is the impact ionization coefficient for electrons, is much greater compared to the impact ionization coefficient of holes. Alpha E by alpha H is of the order of 30 for a field, when the applied field in this medium is of the order of 10 to the power of 5 volt per centimeter. What it means is predominantly the ionization is because of electrons. Electron ionization is almost 30 times efficient, more efficient compared to secondary pair generation due to holes. So, the efficient avalanche process is by electrons, and to make use of this fact, a new design of APD has been proposed, and this is currently widely used design for APD, which is called the reach through APD. We see what is this reach through APD. Here is the APD structure, a high n plus region, then a p region here, and pi, that is low doped near intrinsic or low doped region here, p, and then this is the p plus, high p. So, because of a large n plus, so there is a reverse bias here applied, because of high doping concentration here, at this junction, close to the junction, we have large density of immobile positive ions, because the electrons have migrated here, and large density of immobile positive ions. Therefore, if we plot the electric field variation in this direction here, this is the direction corresponding to this, the electric field rises rapidly and is very high around this junction. Electric field is very high. We can see here that it is approaching, the peak value is approaching 10 to the power of 6 volts per centimeter. So, this shaded region is the region where the electric field is above 10 power 5 volt per centimeter, where the avalanche process takes place. That is the kind of field that is required for avalanche process to take place, and the field drops down rapidly, because we have already discussed the field E is nothing but rho times dx, rho is the charge density here. So, carrier charge density. So, it drops down because on the p side there are negatively charged immobile ions. So, the sum drops down. So, electric field drops down further and it drops down here, and in the pi region there are both negative and positively charged immobile ions, and therefore, the electric field almost remains constant in this region as you integrate rho dx. So, the electric field almost remains constant. Actually, there is a small slope here, there is a small slope which is sloping down like this here, but it is not shown here, it looks almost as if it is flat, there is a small slope. But the important point to see is the electric field here is much lower than 10 to the power of 5 volt per centimeter. In this region, the electric field is higher than 10 to the power of 5 volt per centimeter, in this region the electric field is much lower. Because the electric field is much lower, any carrier which is in this region accelerating either to this side or to this side will not be able to have enough kinetic energy to create additional electron hole pairs. Please see that in this design, this is primarily the catchment area. The photons are incident in this region, photons are absorbed primarily in this region. This is not correct exactly to scale, because the thickness of this region, and this region are much smaller compared to the thickness here, much smaller. So, the photon, the light which is incident on the photodetector is primarily absorbed in this region. There are electrons and holes which are created in this region. So, this is why I call it as the catchment area, and the electrons get accelerated in this direction, holes get accelerated in this direction because of the electric field. However, the electric field in this region, that is in this region, is not strong enough to accelerate the electrons to energies where they can generate additional electron hole pairs, or there is no avalanche process taking place in this region. However, when the electron accelerating in this region enters this zone here, we note that the electric field is very high in this zone, and therefore, the electron immediately creates very large number of electron hole pairs by impact ionization. The electrons which are the secondary electrons which are generated are further accelerated and collected by the electrode here. The hole which is generated move into this direction, in this direction, but they are moving in a region where the electric field is much smaller, or electric field is not strong enough to create additional avalanche process. And therefore, this means that the avalanche process in this design of this structure is primarily due to electrons. So, the avalanche multiplication is primarily by one type of carrier, namely electrons. This leads to much lower noise figures. In fact, if we look at the previous diagram here, please see that a carrier pair generated here, electron gets accelerated in this direction, hole gets accelerated in this direction. As the electron proceeds, it creates additional electron hole pairs, and the hole which proceeding in this direction creates additional electron hole pairs. So, an electron which is created here, electron hole pair, electron moving in this direction will keep on creating additional electron hole pairs. Similarly, a hole which is generated here will, as it accelerates in this direction, it creates additional electron hole pairs. The process would continue almost unabated even if the incident light is just an impulse or a pulse. It appears as if the process would continuously continue, or it is never ending. However, in practice it does quench after a relatively long time. Whereas, if you create in the next design, in the reach through APD design, since the avalanche process is taking place only at this end, the electrons, secondary electrons created are immediately collected here. The holes which are created are moving in this direction, but they are not creating any further avalanche, and therefore, the quenching of the avalanche process, that is stopping of the avalanche process soon after the light pulse has been switched off, or light pulse is absorbed, will be very rapid. So, let me illustrate what I have been saying. So, let me just illustrate what it means. So, if I have, let us say, an incident pulse this is an optical pulse which is incident on the photodetector. So, this is time axis and this is of course, the light energy or intensity I of t. So, this is the incident pulse on the photodetector. The current response of the photodetector, if I take an APD. So, because of the pulse, so this right now I am plotting APD current I of t. Ideally, when the intensity goes up, I should have the current going up like this, and when the intensity comes down, current should come down. This means if the detector is responding fast enough, that means the current pulse which is generated is identical to the input optical pulse. However, in general there is a delay, because even after the pulse disappears, that is in time, even after the pulse is absorbed or the light pulse is no more there, it takes some time for the carriers to recombine and the current to come down. In other words, the current pulse. So, this is, so what I have shown here is the incident optical pulse, and ideally I should get the current pulse like this. However, in practice what we see is there is a finite time over which the pulse continues even after the incident pulse is pulse has been absorbed or pulse has passed through. So, this tail here is because of the carriers which are there in the medium, or with reference to the avalanche process, this corresponds to this a rapid drop or a drop which is slow here, corresponds to how fast the avalanche process quenches. So, this is slow, which means the avalanche process takes longer time to quench or to stop, whereas in this case it is faster, this is faster. So, the reach through APD ensures that the avalanche process is primarily due to electrons and electron mobility is much higher, and therefore, the current drops down rapidly and the device becomes faster. So, this is what I was referring to with the fast and slow detector. Okay. So, let me show the current gain characteristics for a typical silicon reach through APD N p pi p plus. So, at 0 degree centigrade, as we have already discussed this, as the temperature increases because of more number of collisions, the carriers which undergo more number of collisions with the atoms in the lattice, the distance, the average distance between two collisions is much smaller, and therefore, they do not have sufficient time, they do not have enough time to gain kinetic energy and create additional avalanche processes, and therefore, as temperature increases, the current gain drops down. However, as voltage increases further, the kinetic energy gained becomes sufficiently large, and then it leads to a higher current gain. This is a characteristic which shows the wavelength dependence of current gain, a typical silicon APD current gain here, and you see that at lower wavelength here, at lower wavelengths the current gain is smaller, and as the wavelength increases up to around 1 micron or 1000 nanometer, the current gain increases. This increase is this low value of current gain and higher values of current gain here are primarily because of the quantum efficiency. We know that the quantum efficiency of silicon, we have already seen this in one of the earlier curves, or maybe let me show right here. We have seen the quantum efficiency here. So, silicon here has a smaller quantum efficiency at lower wavelengths, and the quantum efficiency here is relatively large. The responsivity is large as the wavelength increases. Of course, once as we reach the near the band gap wavelength, the quantum efficiency drops down, and this is the primary reason for the characteristic that I have just shown, that is dependence of current gain on wavelength. So, finally, we come to some generic parameters of silicon, germanium and indium gallium arsenide pin photodiodes. So, if you take a typical data sheet, this is the kind of numbers that you would see. Wavelength range, that is wavelength range over which this is the detector is useful operating wavelength range, lambda here in nanometers. Silicon, it is around 400 to 1100. So, we have discussed this in detail. So, this is primarily because of eta or the quantum efficiency of the detector, whereas germanium can germanium has a smaller band gap, and therefore, it is a useful detector in this range 800 to 1650 or maybe 1700, whereas indium gallium arsenide is primarily a good detector in this wavelength range, and that covers the optical fiber communication window, and as we have seen, as we have discussed earlier, this is the detector which is widely used in optical fiber communication. The responsivity, typical numbers are here, amperes per watt, it is current generated per optical power incident, that is why amperes per watt. So, typical numbers 0.4 to 0.6, 0.4 to 0.5 and 0.75 to 0.95. The responsivity is quite high. Dark current here in nanoamperes 1 to 10, 50 to 500 and 0.5 to 2 is the dark current, typical dark current for detectors. Of course, it depends on the material, the process and the device structure, but these are some typical generic parameters. The rise time here typically 0.5 to 1 or even 0.1 silicon detectors and 0.1 to 0.5, and one can have detectors with the 0.05 to 0.5 nanosecond rise time of the photodetectors. Bandwidth, that is the detection bandwidth in gigahertz. So, this is primarily inverse of the TR here of the order. The bandwidth is detection bandwidth is of the order of just under 1 gigahertz, here of the order of gigahertz and of the order of gigahertz. The bandwidth is almost similar. It, as you can see, it is primarily depending on the inverse of the rise time, how fast a detector is, and the bias voltage for pin photodiodes, typical biases are between 5 and 10 volts. Normally, they are reverse biased with 5 to 10 volts. Generic parameters of silicon, germanium and indium gallium arsenide APDs. The wavelength range again is the same, is listed the same wavelength range. Main difference is the avalanche gain. We have current gain here, typically 20 to 400, 50 to 200, 10 to 40. Of course, it depends on the operating voltage, but this is the range of gain typically of the order of 100 is the current gain which is employed in practice, and the dark currents are again listed here. The dark currents in this case, as you can see, are relatively large because you have applied a larger reverse voltage corresponding to at a gain of m is equal to 10, current gain m is equal to 10. The rise times are typically sub nanosecond, fraction of nanosecond here, and the gain bandwidth is again similar numbers, hundreds of megahertz to few gigahertz, and one can have detectors with very large bandwidth, and the bias voltages, as you can see, earlier we had 5 to 10 volts, but now we have bias voltages of 50, 100, typically tens of volts, or silicon for example can withstand much higher reverse biases, and that is why we have typical operating voltages of about 250 for silicon, but relatively lower operating voltages for germanium and indium gallium arsenide. We know that they have a much smaller band gap, and therefore, you cannot apply very large reverse bias that could lead to breakdown of the device. I think with that we come to the end of this talk on photodetectors. Silicon and germanium and indium gallium arsenide photodetectors widely used in optoelectronics and optical communication. Most of them are pin diodes or APDs if you need gain. When you have gain with the avalanche process, normally there is additional noise. Noise is a topic which we have not discussed in any detail. I will stop this talk at this point. In the next lecture, we will discuss about some of the other detectors, other photodetectors, including the PMT. I briefly mentioned about PMT, which is widely used. We will discuss about PMT and miscellaneous detectors in the next class. So, today I will stop at this point.